Hello and welcome back. In this video we will be concluding section 5.1 jointly distributed random variables, and in this video we'll be emphasizing independence. So to begin with, let capital X and capital Y be discrete random variables. Then we define capital X and capital Y to be independent if the following condition holds. The joint probability mass function, so little p of x comma y, is equal to the product of the marginal probability mass functions with respect to x and respect to y, just like so. Similarly, if capital X and capital Y are continuous random variables, then capital X and capital Y are defined as independent if the joint PDF of X and Y is given by the product of marginal PDFs of X and Y respectively. So we have a definition for independence of events, and we're going to see that this is correlated to the independence of two random variables. So to see this, suppose that capital X and capital Y are continuous independent random variables. So I'm just going to assume the second here. So we're going to deal with integrals as opposed to sums. And let's consider the case of the following event. So this is the event that, or the probability of the following event, that capital X obtains a value on the interval from A to B, and capital Y obtains a value that's on the interval from C to D. Well, by definition of the joint PDF, this is the integral, the double integral defined like so. Just as follows. Well, since capital X and capital Y are independent, we can express the joint PDF as the product of marginal PDFs. So if we look at this first integral, again, I'd like to try to break this up into pieces. And we can notice that inside this first integral, the function f sub capital X of x, or this marginal PDF with respect to the variable capital X, is only a function of little x. So it can be pulled out of that first integral. Giving us the following expression. Also, this first integral here, this inside integral in the parentheses, is going to be just a number. Since we've removed all expressions of x outside of it, this is actually just going to be a number, a constant. So it can be pulled outside of the outside integral, leaving us with the following. Now, by definition of the marginal PDFs, this is just equal to probability, the first integral here is just the probability that capital X takes on a value that falls on the interval from A to B. Similarly, this second term is the probability that capital Y takes on a value on the interval from C to D. So in conclusion, the probability of the intersection of these two events, because that's what these are, these defined events, these restrictions on the random variables capital X and capital Y define two events. And remember, comma just means and. So in other words, this is just another way to write intersection. And we've concluded that it is the product of the two events. So in other words, the two events defined by the random variables capital X and capital Y are independent events. So that's a very natural way to define random variables as being independent. So let's look at an example. So this is the example that was done in the last video. And to remind ourselves what this is, two components of a mini computer have the following joint PDF for their lifetimes capital X and capital Y. So this gives if capital X and capital Y are the lifetime of these two components, they can be interpreted as random variables, and it's given by the following. So in this sense, the lifetimes of capital X and capital Y are dependent upon one another, given by this joint PDF. So our question is, which is part D in the question for anyone who's interested, are capital X and capital Y independent random variables? So are these independent? So to see the solution, from last time we had the following. By definition of the joint PDF of capital X, or in short, just the PDF of capital X, is given by the following integral. Now, even though this looks like an expression of two variables, I again emphasize this resulting expression is just an expression of x because y is now a dummy variable, since we're integrating this expression with respect to y. Last time we saw that this defines the following piecewise defined function. E to the negative x when x is greater than 0, and 0 otherwise. So notice we did not have this when x is greater than or equal to 0, because when x is equal to 0, f of x comma y is also equal to 0. Therefore, this integral must be equal to 0. We can see clearly that if we plug in x equals 0 here, we do not get back 0, we get back 1. So therefore, this is only true for x greater than 0. Similarly, this is the integral from negative infinity to infinity, but with respect to x this time, and it's given by the following piecewise defined function. So in this case, we did pick up the value 0 for y, and it's given by this piecewise defined function. So therefore, their product the product of the two joint PDFs is given by the following expression. In the case that x is bigger than 0 and y is bigger than or equal to 0, the product of these two things is the following expression. So it's this thing when x equals greater than 0 and y is bigger than or equal to 0, and 0 otherwise. And we can see that this is clearly not the same as our original joint PDF. So this is not equal to f of xy. So therefore we conclude capital X are not independent. So one giveaway to this, so we went through kind of the long way. We computed in the previous video the marginal PDFs for capital X and capital Y respectively. And directly by taking the product, we can see it's not equal to the joint PDF. However, if we look at the joint PDF, we can see that this is not a product of a function of x times a function of y. And we can see this inside the exponent here. So the exponent is a product of x times the quantity 1 plus y. There's no way to break this up. So it's a function of x times a function of y. So therefore, this has no chance of being independent. The capital X and capital Y have no chance of being independent because of this. However, we can see directly that clearly our independence relation fails. Independence criteria. So that is independence. For future sections, it'll be important to consider more than two random variables. So we're going to talk about independence of a set of random variables. And to do this, we need the following pieces. So if x sub 1, x sub 2, all the way up to x sub n, so we have n random variables, or discrete random variables, then we have the following definition of the joint PMF, or joint probability mass function. That is the probability of x sub 1, x sub 2, x sub n. So this is a function, so a scalar function with n arguments. This, by definition, is the probability that the random variable capital X sub 1 is equal to the value little x sub 1, capital X sub 2 is equal to little x sub 2, so on and so forth. And it's given like so. Similarly, if x sub 1 through capital X sub n are continuous random variables, then the joint PDF is a function of n arguments, x sub 1, x sub 2, all the way up to x sub n, where for our intervals, a1 to b1, a sub 2 to b sub 2, all the way to a sub n to b sub n, we have the following. The probability that our first random variable falls on the first interval and our second random variable falls on the second interval all the way to the last interval. This is equal to the integral from a sub 1 to b sub 1 n integrals are here. So it's not it's a double integral in the case n is equal to 2, a triple integral in the case that n is equal to 3. So in general, it's a nth integral. And our order of integration is reversed because we're doing the inside integral first. So that's respect to the nth variable. Okay, so let's integrate with respect to dxn. The next integral on the outside is dxn minus 1 all the way out to the outside integral, which is in respect to our first variable x sub 1. Okay, so in other words, these are thought of as volumes in Rn. Okay, so we're integrating over regions, or this is a box or a cube in Rn, or an n-dimensional cube if you'd like. So this is how we define probability, or the distribution of n random variables. The random variables, which is kind of squeezed in here now, x sub 1, x sub 2, all the way up to x sub n, are defined to be independent if for any subset of k random variables from above. So we can denote these by x sub I sub 1, x sub I sub 2, all the way up to x sub I sub k. So in the case that k is equal to 2, this is some subset of 2 random variables of these n random variables. So it might be x sub 1, x sub 2. It could be x sub 1, x sub 3, x sub 2, x sub n. But in the case where k is equal to 2, we take 2 random variables from above. When k is equal to 3, this is a subset of 3 random variables. So this is a subset of 3 random variables from above. So in general, we're going to let x sub I sub 1, x sub I sub 2, all the way out to x sub I sub k be any such given subset of k random variables from above. The joint PMF or joint PDF, depending on if these random variables are continuous or discrete, is denoted by the following. So we'll do the joint PMF, and I'm denoting this by p sub x sub I sub 1, comma x sub I sub 2, to emphasize that this is all the way out to x sub I sub k, to indicate that this is the joint PMF, or the joint PMF function, probability mass function, of these k random variables. Okay, so it looks just like above here, but it's, in the case, it's such a function for these k random variables. And that such a function needs to have this property. The joint PMF needs to be the product of their marginal probability mass functions. So they look like capital P's, but these are little p's. In other words, this is just the probability mass function of x sub I sub 1. This is just the probability mass function of x sub I sub 2, and so on and so forth. Similarly, so this is in the case that the x sub 1 through x sub n are discrete. If x sub 1 through x sub n are continuous, then the joint PDF of those k random variables from above, so this subset of k random variables, is going to be a function of k arguments And the notation is mimicking the notation from above here. This is going to be equal to the product of their marginal PDFs. So this definition of independence correlates with the definition of independence of n events, but carries over to random variables. So I won't go into details on this. This is our definition. It turns out to how the derivation of just two random variables can be extended to n random variables here. So these definitions will be helpful in later sections when we start talking about sequences of n random variables being independent. So that's the end of this video. We will continue on with section 5.2, which is over the mean and variance of random variables.